Welcome to the video lecture of Compiler Design. This video discusses the evaluation of attribute part 2 of module 4. Let us recall the syllabus of module 4 once again. Already posted the videos of syntax related definition, bottom up evaluation of S attribute definition, L attribute definition, and top down translation. This video is discussing on the topic bottom up evaluation of S inherited attribute. Coming to the topic bottom-up evaluation of inherited attribute, it presents a method to implement the L attributed definition in the framework of bottom-up parsing. L attributed definition means basically it is left attributed. That means L attributed definition means it consists of inherited attribute. It has some restriction. The restriction includes it can inherit either from its parent or from its left sibling. That means it follows a pre-order form of traversal while it constructs the parse tree during the evaluation of attributes. So we can say that this L attribute definition is more suited for top-down parsing, but here we are presenting a method so that we can implement L attribute definition even using a bottom-up parsing framework. It can implement any L attribute definition based on LL1 grammar. It can also implement many L attributed definition but not all based on LR1 grammar because LL1 grammar itself is a subset of LR1 grammar. Moving to the details, removing embedded action from translation scheme is the first subtopic of bottom-up evaluation of inherited attribute. So what do you mean by removing embedded action from translation scheme? We can see with the help of an example. Consider E gives tr, the production E gives tr, R gives plus t, R, and R gives minus t, R gives epsilon. In this, the productions are embedded within the symbols between the RHS of the productions. So these syntax directed translations can be excluded. Instead of this, we can provide markers. So that is what we are explaining in this slide. Make transformations so that embedded action occur only at the end of the production and replace each action by a distinct marker non-terminal M and attach action at end of M gives epsilon. That means we are by introducing a marker instead of translation and we are including actions at the end of the production. End of productions of the marker symbols. So again consider this example. The above grammar which has got translation scheme gets transformed to this set of production which has included markers in its production. So instead of this print plus, which is a translation scheme, we have introduced a marker called capital M. Then instead of print minus, we have introduced another marker called capital N. Then similarly for t gives num, print num dot well. It is not necessary to remove that because it is already at the end of the production. So M gives epsilon. At the end of this production of this new marker, we have to introduce the action which we have replaced with. So N gives epsilon, its corresponding action. So this is an example where we can replace the translation scheme which is embedded within the or between the symbols on the right hand side of a production. While we introduce the markers, we have to introduce new productions for that markers like that marker symbol gives epsilon. So always in transformed production with markers, the actions will be at the right hand side of the productions. Next topic of bottom-up evaluation of inherited attribute is inheriting attribute on parser stack. So how we can use the stack implementation of parser for evaluating the inherited attribute. Here, bottom-up parser reduces RHS of A gives X, Y by removing XY from the stack and putting A on the stack. That is the basic shift reduce principle. Synthesized attribute of x's can be inherited by y by using the copy rule y dot I equal to x dot s. If y is an inherited attribute, x is having a synthesized attribute, y can copy the synthesized attribute value of x by using this statement. Consider again the example of declaration. D gives TL. You consider the string real p, q, r. The production corresponding to this declaration are D gives TL, T gives N, T gives real, L gives L, ID, L gives ID. Inside this also the actions are also embedded. Translation schemes are embedded, so that we can build the code fragment so that we can evaluate the value of attribute. So this is the example of a stack parsing the string real p, q, r based on the productions or the translation scheme we have already discussed in the previous slide. So while we consider the string real p, q, r, since we are going to perform a bottom-up parsing, means identifying the handle, and if the handle is on the stack top, we have to reduce it, otherwise we have to shift the symbols onto the stack. So the same thing we have to perform. Basically, bottom-up parsing is a rightmost derivation reverse order. So initially you find the rightmost derivation, D is TL. In the production, D is TL. We have expanded the start symbol capital D. Then again this rightmost non-terminal is L, that is replaced with L, R. L, ID, instead of ID we are directly giving the R, Q and P values. Again this rightmost non-terminal is capital S, it is replaced with the L, Q. Again using the production L gives L, Q. Then again L is replaced with L gives ID, so that is in the case of ID, here it is P. Then again the T is the left and rightmost non-terminal pending, so that will be replaced with the real. T is real. So we will be ending up with real p, q, r during rightmost derivation starting from the D. So this rightmost derivation reverse order will be used in shift reduce parsing. Here the same stack is shown. Here also only the stack symbols are grammar symbols are shown, and the input is having only input is shown, then its corresponding action. So initially the input is having a real. We can reduce only if when there is a handle is over the stack top. So first handle we are expecting is real. So otherwise, if that means if it is not a handle on the stack top, we have to shift the input onto the stack. So real we have pushed onto the stack. Now the real is on the stack top, that is the handle. Then we have to replace it with the T. That is shown here. T is real. Real is replaced with T. Then again the stack top is having T. What is the next expected handle? P. So P is the handle. So since only T is here, no P, so we have to shift this input. So P. Now P is on the stack top. P is the next expected handle. So we will reduce the P using the production L is ID. So P is replaced with L. Then again the next one we are expecting is L, Q. So currently the stack top is having P. It is not a handle, so shift. So L, currently the stack top is having L and it is not a handle, so shift, comma. Then comma is on the stack top, it is not a handle, only L, Q is the handle, so you have to push the shift the Q also onto the stack. So Q is shifted onto the stack. Then after that, we can see that L comma Q is the handle, so we can reduce it using the production. L gives L comma ID, so it is replaced with the L. Then again we are expecting the handle as L comma R. So on seeing in L comma R only we can reduce. So until then you have to, till then you have to shift onto the stack. So comma is shifted, R is shifted, L comma R is shifted using L comma ID. So now L is on the stack top, and the next expected handle is TL. Now TL is on the stack top, reduce it, so D is TL, and finally we have reached the start symbol. But one thing we can notice is that every time a string is reduced to L, T dot val is just below it on the stack. That means wherever this reduction happens, L gives ID. L below, just below it, there is the T with its attribute value. Whereas when we replace L gives L comma ID, there is also a T behind it. That is what we are explaining in the next slide. Every time a reduction to L is made, value of T type is just below it. Use the fact that T dot val is at a known place in the stack. So it is easy to compute the value of the attribute if we have known the place where T dot value is stored as a prior information. So when a production L gives ID is applied, ID dot entry is at the top of the stack and T dot type is just below it. Therefore, so what is our aim? Aim is to write the code fragment corresponding to the std so that it can perform a translation so that it can output the value of attribute. So here in the case of syntax error definition corresponding to this production, the syntax error definition is add type id.entry l.in. That can be replaced with the code fragment add type val of top. That id.entry, now it is the id is at the top, stack top, and immediately below the stack top there will be that type. L.n is actually the type value. It is inheriting the value of T. Similarly, in the case of L gives L comma ID, we can replace that add type id.entry comma L.n as add type val of top comma val of top minus 3. Because it is L comma ID. ID is at the top, then top minus 1, then minus 2. So top minus 3 should be having the value of T. So we can see that the translation scheme, the code fragment for the translation scheme will look like this. Val of top equal to integer, val of top equal to real, add type of val top comma val top minus 3, in this case val of top comma val of top minus 1. Next subtopic is simulating the evaluation of inherited attribute. This scheme works only if grammar allows position of attribute to be predicted. That is the important point in this. Consider the grammar. S gives small a, small capital C, Ci equal to As, I stands for inherited, S for synthesized attribute. S gives B, capital A, capital B, capital C, Ci equal to As. C gives small c, Cs equal to G of Ci. C inherit As. The inherited attribute, it is getting its value from A. Inherited attribute is valid from A. Getting it valid from A. This CS, it is computing the synthesized attribute from this C. Right. So we can, while we listen into these two production, there may or may not be a B between A and C on the stack. When reduction by rule, C gives C takes place. So whenever the C will be seen, this reduction will be when small c will be seen, it will be reduced to capital C. So that time immediately below the value of A will be there. So when reduction by C gives C is performed, the value of Ci is either in top minus 1 or top minus 2. Either in top minus 1 or top minus 2. So we should be aware that where that value will be there prior to the parsing. it is continued by inserting a marker so that the position could be arranged as same. S gives A, C, B, A, B and C. Here we have introduced a marker. We have introduced the rules also, Mi equal to As, Ci equal to Ms, and whenever we introduce a marker, we have to introduce that M gives epsilon, that Ms equal to Mi. When production M gives epsilon is applied, we have Ms equal to Mi, that is equal to As. So it is coming from this As to Mi to Ms, and from that it is going to Ci. So therefore the value of Ci is always at the top minus 1. So A will be at the top minus Ci equal to As. Then here Ci is equal to Ms. Ms means Ms contain the value of As, because As is copied to Mi, Mi is copied to Ms. So Ms contain the value of As, which is actually below the C. So for both the production we can write it as it is at top minus 1. Then markers also can be used to simulate the rules that are not copy rules. In the previous slide it is copy rule, Ci equal to As. Just copying, assigning the value. Now we are examining that it is not a copy rule, it is a rule based on function f. How we can use a marker here. S is A and C. N is the marker. N C. Then N is the marker. N gives epsilon as the production. Its corresponding rule is also here. So such that like that way we can simulate the evaluation of attributes, the inherited attribute, using a bottom-up parser. Next slide explains the general algorithm which is explained with the help of the procedure. Input is L attribute definition. Output is a parser which can compute values of all attribute on its parsing stack. Whether it is synthesized or inherited attribute, it can compute the value of all its attributes on the parser stack. So method, it is asking us to assume every non-terminal has one inherited attribute and every grammar symbol has a synthesized attribute. These all things here we have to keep in mind while we use a parser whose input is supplied as an L attribute definition. That means L attribute definition means it is basically a grammar which can be ready to be parsed through a predictive parser, a top-down parser. But here we need a parser that can compute all type of attribute. That means both synthesized and inherited. So that means we need a parser which can traverse in depth first order. So and after constructing the parse tree, it should evaluate all the values of the attributes also. So here we are assuming some statements for that. That is, every non-terminal has one inherited attribute and every grammar symbol has a synthesized attribute. For every production A gives x1 etc xn, introduce n markers m1 etc mn and replace the production by A gives m1 x1 etc mn xn. To introduce the markers, we have already seen this, and whenever the markers are introduced, we have to introduce the production m1 etc mn gives epsilon. Synthesized attribute goes into the value entry of xj, and inherited attribute, it will go into the value of entry of mj. That is the important thing we have to remember. So whenever the reduction is made to a marker mj and the marker belongs to the production A gives m1 x1 etc mn xn, then ai will be in the position top minus 2j plus 2 and x1 dot I will be in top minus 2j plus 3, x1 dot s will be in top minus 2j plus 4. If the reduction is to a non-terminal A by production A gives m1 x1 etc mn xn, this can be explained so as to compute As can be explained with the help of this diagram. Currently the A gives m1 x1 etc mj xj. So already the thing told is that A is having the inherited attribute is stored before x1. So corresponding to A inherited attribute. Then A is m1 x1. So x1's inherited attribute is stored along with m1. x1 synthesized attribute is stored along with x1. Like that till mj minus 1 xj is storing xj inherited attribute of xj minus 1 and synthesized attribute of xj minus 1 is stored along with this. Here we are computing the inherited attribute of xj dot I that will be stored with the mj. After reducing mj with the mj gives epsilon. So here we are assuming that here in xj minus 1. So if the top is at xj minus 1, A will be stored in top minus 2j plus 2. And this is top minus 2j, 2 minus 2j plus 2 will be storing the inherited attribute of capital A. And just above that, x1's inherited attribute should be stored. That is why it is shown as top minus 2j plus 3 plus 4 its synthesized attribute. Again plus 5 like that it continues. So if reduction is made, mj gives epsilon. That means on seeing the epsilon should be replaced with mj and mj should hold the inherited attribute of xj. Then the new stack top will become this one. Here one thing you have to remember is that we have supplied as input the L attributed definition, which is actually ready for top-down parsing. So how that got reduced, m gives epsilon got reduced. So that is the thing that we have explained. If we are given an input L attributed definition, we are going to create a parser that can evaluate both synthesized and inherited attribute, which can perform a bottom-up parsing. That means even the reduction can take place. So we are saying that, or we are concluding that LL1 grammar is a subset of LR1 grammar. So bottom-up parsing is possible for that. That is the next slide. If one more slide is before that, xj has no inherited attribute. Some more simplification we have do to this algorithm. If xj has no inherited attribute, need not use marker mj. It is better to avoid markers. Even if an inherited attribute occurs, and if that inherited attribute is just based on a copy rule, we can avoid that markers because we know that already A is having only inherited attribute. We are assuming like that, and that inherited attribute will stay just beyond the x1 on the stack. So there is no need to show it using a marker. So the conclusion is that using a top-down translation scheme, we can implement any L attribute definition based on LL1 grammar that we have already learned in the previous presentation, evaluation of attribute part 1. Here using a bottom-up translation scheme, we can also implement any L attribute definition based on an LL1 grammar. Each LL1 grammar is also an LR1 grammar. So even if the input is an L attribute definition, which is actually LL1 grammar, it can be passed through a bottom-up parser LR1 grammar so that it can perform bottom-up translation, so that it can evaluate the values of both synthesized and inherited attribute, especially the L attribute definition, which is having some restriction over the inherited attribute. Thank you.